Welcome. In this video, we'll discuss section 5.5, linear combinations, part 2. So in the last video, we talked about a set of n random variables and generalized this idea of a joint PDF that we talked before. And we'd like to, in this video, talk about the covariance operator and some of its characteristics. So to begin with, let x sub 1 through x sub n be n random variables, all on the same sample space S. And this has joint PDF F going from Rn to R. So the way to interpret this is that F is a scalar function that takes n-dimensional vectors as an input and gives us back a real number as an output. So for notation, let capital X with a vector sign over it denote a random vector where the first component, x1, is the random variable of the first component, x sub 2 is the random variable of the second component, and x sub n is the random variable of the last component. And also consider a region A that sits inside of Rn. So the idea to interpret this random vector is the following, or this joint PDF. The probability that our random vector with these components takes on a value that is an element of the region A is equal to the n-dimensional integral over the region A of our joint PDF f vector x dx. And last time we said that this is notation for the n-dimensional integral over A, x1, x2, xn, looking as follows. So therefore dx vector hat is just this differential volume sitting in Rn. Similarly, if we let h be any integrable function going from Rn into R, then the expectation of h of x we define to be, this defines a new random variable. We define this to be just like so. So capital X is replaced by little x. That's a little, this is a capital. Kind of hard to see that. Looks like this. So that's big X, this is little x. It looks just like the following. So we went over these things in the last video, and we ended up with the following proposition. And so this is actually a generalization of the proposition we gave in the last video. But let h sub I be a scalar function on Rn for each I going from 1 up to some value k. It doesn't matter what k is. K is independent of n here. So these are just k scalar functions on Rn. We can define a new random variable, y sub I, is equal to h sub I of the random vector x. So this defines a new random variable for each I. Again, where our random vector is defined using our n random variables. Then it follows that the expectation of the sum from I equals 1 to m So the expectation of a linear combination of the yi's is the linear combination of the expectations of the yi's. In other words, the expectation operator can be applied or distributes over linear combinations. So in the last video, we showed this is true for x sub i's, but this is a little bit more general of a statement. Any random variables that we make y sub I in terms of these scalar functions has the same property. And the proof is identical. It's just we're using y sub i's instead of h's, or instead of x's. So in this video, so that's what we had. This kind of a quick reminder of what we covered in the first video. So let's just consider the case where we have two scalar functions given like so. So h1 and h2, just like how we defined up above. Also, actually, never mind on that. So we have these two scalar functions. We can define the following. The covariance this is equal to the expectation so these are capitals in there. So a lot of parentheses, but defined just as follows. So it's just like the covariance operator for two random variables, we can define it in terms of just two new random variables defined on the n previous random variables. So this is our definition of covariance. And we have the following proposition. So this is going to be for the rest of the video, we're going to show the following, is that the linearity of the covariance operator in each of the components carries over even in general when we have several random variables. So let h sub I be a scalar function from Rn to R for I is equal to 1 through k and including k plus 1. And let's define the following random variables. Let y sub phi be equal to h sub I of the random vector x, and this is for I going from 1 up to k, and also define z h sub k plus 1 of the random vector x. So this is going to be for notational purposes. So in other words, we have these k plus 1 scalar functions on Rn, and using those k plus 1 functions, we can define a new random variable for each function. So using each function. And also this other random variable z. Then we have the following three properties of covariance. One, like so. So all the yi's, we've defined k new random variables, doesn't matter what k is independent of n here. And the covariance operator is symmetric on these random variables. It doesn't matter what I and j are. So j is also in that bound. Doesn't matter what they are, it's symmetric. 2 is that the covariance operator is linear in the first component. In other words, the covariance of a linear combination is the linear combination of covariance where the second component remains fixed. So in other words, covariance distributes over linear combinations in the first component. Putting 1 and 2 together, we have 3. Oh, these are not n, this is to k. I apologize, not n to k. Just like so. So property 3 says the covariance operator is also linear in the second component. So just a note here, properties 1 and 3 I will not prove. Property 1 follows immediately from the definition. We can see it's symmetric in the argument, so I can swap these two around and I get the same thing. And using that fact, you can quickly deduce from 2 that 3 must also hold. So I will only be proving property 2 here. So to prove this, we'll start with property 2. Up to k, a sub I, y sub I, and z. And really at this point, the y sub i's are just for notation. We are going to rely solely on the linearity of the expectation operator. So in other words, proposition 1. And so by definition, this is equal to the expectation of the following. This defines a random variable. So it's the sum like so, multiplied by this is just the definition of the covariance of these two random variables. So even though this is a sum of random variables, it is a random variable itself. By the linearity of the expectation operator, the expectation can be distributed over the sum, giving us the following. Just like so. Combining these two sums term by term, so all the I terms are combined, and factoring out the common term of the a sub I, we have the following. just like so. So a number of parentheses here. The next step that we'll do is that we'll distribute this expression over each term in the sum, giving us the following. Giving us the following expression. So the inside here is just another random variable, but ultimately a random variable defined by the random variables x sub 1 through x sub n. So therefore, the expectation operator distributes over this sum. So using the linearity of the expectation operator, we have the sum I equals 1 to k. Just like so. And by definition, this is for each value I, this is the covariance of y sub I with z. And this completes the proof. So again, this is just proof for statement 2 of that proposition. So in the next video, so between videos 1 and 2, we've now generalized all of our results. So the linearity of the expectation operator and the bilinearity of the covariance operator in each of its components to the general case in which we have a sequence of n random variables. In the next video and the last video, we'll talk about further properties of the covariance operator in the case that the x sub i's are independent.